this is like a scratch thing. It's not going to be an official video for section 8.5. And it's just like only about the pH curve and how can I represent them, etc. So we start with the first case, which is a strong acid with a strong base. Okay, strong base. I'm so sorry for my handwriting, you know, like it sucks. So first of all, since we have I have a system of titration, we're going to add acid to base or base to acid, etc. So here, suppose that we have a base in the puree and we have an acid. I start to make titrations. I have the pH meter inserted and like the flask, and you can see that since we have acid and the pH is inserted in, it reads the low values. So if I want to represent that in terms of a graph, I have to say y-axis, x-axis for sure. The one that is in the puree will be the x-axis, which is the volume of base in milliliter. Okay, and since we're adding base, we're expecting to have elevation and the pH values. So we started with a very low pH. The pH, by the way, this is on the y-axis. We start with the low pH, and then we have a vertical line, and then we have another horizontal line. So what does this mean? We are reacting the H positive with OH negative until they become equal. Okay, the time at which they become equal is represented in a vertical line in here. At that point, if you want to understand, or let's say to determine the volume at which they become equal, we just look at the vertical line and then see the number below in here. So this number that represented on the x-axis is called the volume of equivalence. So the equivalence point is a point at which the volumes and the acids, like when they're completely react with each other, nothing left behind. And since we have a strong acid and a strong base, we can notice that the pH at the top for base, it's like almost 14 or 13. It's not below. And for the acid, you can see like it's almost 1 or 2 because it's a strong acid. And we just noticed that there is a straight line that takes place in here, like it's almost straight line. We don't have any curves. So this tells me that you have a strong acid in here and we have a strong base. In addition to that, the vertical line, as you can see here, it tells you like the most vertical one will be the strong acid and a strong base. And the last point that you could like just keep in mind, the midpoint on the vertical line tells you that the pH at equivalence point is equal to 7. And this happens only when you have a strong acid and strong base. Suppose that we have weak acid and strong base. What's going to happen? You have to keep in your mind, the weak acid has a special property. It will start with like something like this if we just do it in the middle in here, and then we put it like this. Just keep in mind, we just noticed that we have a curve in here, and it's not the same one as in this strong acid and base. You just notice that in the strong acid it started like this, right? We don't have that curve. So the reason behind this process, or the reason behind this curve, is something called, it's a buffer jump. Okay, it's a buffer jump. So what is the buffer jump? The buffer jump, since we're dealing with weak acid, the weak acid leads to produce a conjugate base, and as a result of the conjugate base, since it's basic, it will have a little bit jump in the pH since the y-axis reads the pH. And just like keep in your mind, as we add a weak acid, it will keep producing conjugate base, and that's why the pH at equivalence is going to be greater than 7 because of the conjugate base produced in the weak acid. The graph itself, you can see like since you have a jump in here, you can determine that this is weak. Okay, the pH is greater than 7 at the equivalence, I mean like the midpoint and the vertical line. And one more thing, if we take a question, for example, suppose that we have a vertical line in here, which means like the V equivalence, let's say 10. If I ask you how can I calculate the pKa for this acid, you have to keep in mind, if I want to calculate the pKa from the graph in here, the volume is 10 milliliters. The half of 10 milliliters is just 5 milliliters. okay? And then you have to take, okay, this is 10, half of 10 is 5, and then you take a vertical log and then see what's going to be the value in here. But you're going to tell me like the values on the y-axis are pHs. Yes, they are pHs, but you have to keep in mind if you do this procedure, the pH is equal to pKa at the point. So for example, if the pKa is 5, then the pH is going to be 5 at this point and here. Okay, 0.3 molar of CH3COOH, which is a weak acid. And we talk like 25 milliliters of this acid for sure, and just like make a titration with sodium hydroxide and AOH, which is the base right here, like the x-axis. My question is, how can I calculate the molarity? I mean the concentration. Okay, how can I calculate the molarity of the NaOH? Well, you have to take this value in here because, you know, like if you want to calculate the molarity, it means that you have to calculate the moles over volume. And since the volume is given to you from the graph, I can take it at a vertical line at equivalence. Then I can say like, yes, everybody's happy. But you have to change it from milliliters into liters by dividing over 1,000. But you'll ask me like, how can I calculate the moles? Just keep in mind, as we have a vertical line in here, it tells you that the moles of OH will be the same as the moles of H positive. And since we're given the number of liters of the acid in addition to their concentration, I can calculate their moles because the moles of H positive are the same as the moles of OH negative. So the moles of weak acid, which is CH3 COOH, is equal to 0.3 molar, which is mole per liter. You multiply it by the number of milliliters, which are 25 over 1,000 liter, and then you will end up with a beautiful number of 0.0075 mole. And this number is the same as the OH. We can substitute it directly and we can say it's 0.0075 mole. Okay, and if you just divide it, the answer is equal to 7.5 molar. Okay, so the concentration, the molarity of the sodium hydroxide is equal to 0.75. We just determine the volume at which they become equivalent to each other. We calculate the value of pKa and the pH at the point. And we just noticed that the pH, since we have weak acid, it's going to be greater than 7 as a result of the conjugate base. So generally, guys, these are the most important things that you have to keep in your mind.